Perfect.
All right, so next talk is Tommaso Cucinozza.
Yeah, right.
We wrote this paper together with Dario Fagioli and Giacomo Bagnoli.
Yes,
right?
perfect.
And by the way, they won the prize for the most complex PDF. So at least my old HP laserjet printer could not print it because there were some graphs in there which exceeded memory, so it just gave up there. But once I did the proceedings, it's printed quite fine. So Tommaso, this one's on real-time or low latency audio on Linux.
Yeah.
Well.
Okay, thank you very much for the introduction. So yes, good morning everybody. I'm Tommaso Cucinotta, and together with the other authors of this work, we come from the Real-Time Systems Lab of Scuola Superiore Sant'Anna. So this is a research institution. So we work on computer science and mainly on real-time issues for embedded systems and sometimes also non-embedded systems. First of all, I have to acknowledge the European Commission with the 7th Framework Program for funding some of our research, thanks to which it is possible for us to participate also into conferences and to carry on some useful work also on Linux. So first of all, I will introduce a few motivations and background of this work. I would say something that, I don't know, might disappoint a few of you. That is the general purpose operating systems, as we know, are very effective for storing and managing multimedia contents. However, they are designed normally for average case performance and for serving applications on a best effort basis. They're not really the best candidate for serving real-time applications. I mean applications with really tight timing constraints where violation of timing constraints should really not happen. Otherwise, the application may be declared as not working. For example, real-time multimedia falls within this class, especially when you go to professional level, professional quality real-time multimedia. Also, whenever we need to compute on a platform with a precise quality of service assurance. However, as we know as well, we do use general purpose operating systems for real-time multimedia. So there are a set of workarounds to this problem. And what are the normal means by which we overcome the limitations of a Gpos for multimedia? Well, first of all, we can use large buffers. So these are used to compensate for the unpredictabilities inherent into the software, into the operating system, into the hardware, whatever. The main drawback of this is that we get only poor real-time interactivity and no low-latency multimedia by this way. For example, on a standard Linux box, we get something like half a second of default delay used for playing back audio, which is quite nice because it allows us to have a skip-free playback of recorded contents. But whenever you need to set up a low-latency box, you need to configure something and to remove this default configuration because that can really create annoyances. Or we also, whenever we use the one application, one system paradigm, we are quite safe because, for example, we can use low latency professional audio processing with Jack, and we can have a box which doesn't have any audio glitches. And also, as we know, we can run a lot of real-time games requiring really fast interactiveness with the user, like gaming, or CD, DVD burning used to be a problem. Nowadays, hardware make us fix the problem anyway. Or plant control in factory automation, where you want to use an OS like Linux, and so on. We can also use POSIX real-time extensions in order to make sure that our time-sensitive critical tasks get run on the CPU before anything else on the system. For example, running our Jack daemon at real-time priority or whatever else at real-time priority. Of course, one of the problems of this approach is that normally we use a scheduler which is priority-based and which provides no temporal isolation. That means that you don't have a way to actually define exactly what is the temporal capsule within which each application should run in such a way that it gets no interference from other applications on the system. So whenever we want to deploy a multitude of soft real-time applications, which are commonplace nowadays in populating our systems, we have a little bit of problems in using these priorities. Imagine you have to deploy multiple of these applications, so you need to understand what priorities to give to each one of these tasks. On a related note, on Linux, we can use a kernel-level extension, which is called real-time throttling. Sometimes it can be useful for, let's say, building these temporal caps, this idea of configuring the scheduling parameters which can be associated to a given process in terms of the amount of CPU it gets. However, this mechanism has been designed mainly for limiting actually a process from running too much in order to not hang up the workstation due to a bug, for example, an infinite loop in a real-time process while debugging a multimedia application that can lock up your workstation. So this is designed for limiting, not for granting. So going back to the problem of how to properly schedule what is instead a real-time scheduler that may properly fit our needs. First of all, I can briefly recall that a POSIX real-time scheduler is simply a multi-queue priority-based scheduler where you may have processes at the same priority which are scheduled round robin or FIFO, depending on the configuration. There's also a standard for the sporadic server extension, which is actually a very useful extension which might fit our needs, but it's not widely implemented, and it's not implemented on Linux, except for our own patch. Also, we know that in traditional real-time systems that make use of priority scheduling, we can make sure that all the deadlines of the real-time tasks are respected by using some, let's say, design or analysis techniques. So if we know, for example, that we have the traditional real-time task model, which is a periodic task that activates at a period T and makes some computation C and then suspends till the next activation. So we have the computation time, or better, the worst case execution time C and the minimum interval period T. Then we can perform an admission control test, which may be as easy as the formula showed on the right. The traditional Euler Island test dating back to the 70s, or the bottom one, the more modern, more accurate, slightly more accurate test found in our lab in the 2000, in the near 2000 years. So we can use some of these tests so as to admit a new application. If this test is passed, we can be sure the application runs without problems, at least for a computing viewpoint. I'm focusing on computing. As you can see, I'm not dealing with problems due to latencies for retrieving data from the disk or similar, or communications like network-based communications and similar. I'm just focusing on computing. So, for example, we may have a situation like the one sketched down in this picture, where we have two tasks on the x-axis. I have the time passing by. The two tasks may be scheduled on the same processor in this way. For example, the high priority task has a computation time of 2 and a period of 6, and the low priority one has a computation time of 4 and a period of 8. As you can see, things work fine because the two tasks are scheduled fine, and they can meet all of the deadlines because they can get the required amount of CPU within the next activation, which is also the deadline of the task. However, as you can know, the problem is that sometimes maybe we don't really have the time to really figure out what is the worst case execution time of a task, or especially in multimedia, we really don't want to mess around with the modern architectures and figuring out what is exactly the worst case execution time. That would take a huge time and also resources, development resources, to understand what it is actually. So we may have actually an estimate, which is a rough estimate, which may not be as accurate. And in the end, we get also some unmodeled interferences from the operating system, which are outside of our control. So we may get a bad job. I call it a bad job simply because its computation time goes beyond what we believed it to be possible as maximum computation time for the task. So this job, as you can see in this picture, this job of the high priority task is misbehaving, and as a result, he's not missing his deadline because it's running at a high priority. However, the lower priority task is actually missing deadlines. So we may have here, a task which is behaving in a weird way, and as a result, you may have deadlines missed by other tasks. This may be good in a traditional embedded real-time arena in which the higher priority corresponds to a higher criticality, and so this situation would be maybe a good one. However, if the two tasks are not really, do not have this criticalness relationship, or I mean, if they have the same importance, if they are both soft real-time tasks that are doing something on the system, and we are all interested in getting them to run in the best way that is possible, then here I can see a problem because the two tasks are not isolated. The one that is running at higher priority will always perform better than the others. So that's basically why there's the underpinning of the motivations that can bring us to the set of real-time schedulers that have been proposed for the Linux kernel in our lab along the last few years. More or less, the features that we used to seek were the ones sketched out here. So temporal isolation between tasks and task groups, the need for provisioning of reservation parameters. So we wanted really to have a sporadic real-time task model where the developer could declare what kind of runtime it needs every period, and the optional allowance to use more CPU if available, which is called also soft reservations in the literature of real-time systems. With a simple admission control scheme, because from the real-time theory, the admission control schemes may become overly complex and also impossible to compute for the computing power of a normal workstation in a reasonable time. So we want simple control schemes that may even be disabled if needed. So also to allow the system to have some optional oversubscription, which may be useful in some cases with a graceful control management of overloads. And also we try to investigate priority-based and deadline-based and mixed scheduling in this context with these features, enriched with hierarchical scheduling whenever possible in such a way that you can define the temporal capsule not for a single thread only of execution, but also for a complex software component involving multiple threads, multiple processes. I mean, something that is not completely defined and defined by us and under our control. Imagine a Java virtual machine to which I want to provide a certain amount of the CPU, or a web server that I want to run with a given QoS assurance.